Yeah. So you're right, the osmotic is going to win, the osmotic's going to pull that fluid back in. What is creating that pull?
Solutes.
Solutes, good. Solutes and proteins are creating that pull, bringing that fluid back into the venous end of the capillary. So at this point, the blood pressure has dropped to a point that it can no longer battle that osmotic pressure. So we've got fluids now returning to the venous end. They told us in this animation about 90% or 9/10 of that fluid is reclaimed back at the venous end of the capillary. Where does filtration occur in a capillary? Arterial end or venous end?
Arterial.
Arterial. What is filtration?
Loss of the fluid pushing.
Yeah, loss of fluid pushing out into the interstitial space. Which pressure is responsible for that filtration process?
Hydrostatic.
Hydrostatic, HPC. The other name for HPC is simply
Blood pressure.
Blood pressure. Okay, so at the arterial end, blood pressure pushes fluids out. Pushing out is called filtration. At the venous end, flip it. What is it?
Reabsorption.
Reabsorption. It's not blood pressure pulling it back in.
Osmotic pressure.
Osmotic pressure is pulling it back in. So actually those solutes and proteins are pulling the water from the surrounding interstitial space back into that vessel. So filtration is out, that's blood pressure. Reabsorption is back in, that's osmotic pressure at the venous end of your capillary. This is setting you up for later on, because later on, I believe it's chapter 25, we talk about fluid electrolyte balance, and we're going to talk about what if you have diarrhea? What if you drink salt water? We'll talk about how that affects the fluids and the solutes in the capillary, and we'll take it one step further. We'll then talk about what it does to the cells and tissues in the surrounding space. So this is something you will definitely see again, so it's critical you get kind of the basis here for what's going on in terms of osmotic and hydrostatic in the battle and who's going to win. Just for fun, let me give a couple of scenarios to you. Let's say a person has a liver disorder. Liver makes albumin and other plasma proteins. Okay? Proteins and solutes are responsible for which type of pressure? Osmotic. Okay. If you've got a liver disorder and you have an osmotic pressure problem, does that result in a filtration issue or a reabsorption issue? Reabsorption. Because what's going to push that fluid out?
HPC.
HPC, hydrostatic. The fluids are just going to be pushed across the wall of that capillary at your arterial end. Why is a liver disorder going to result in a reabsorption issue?
Not enough solutes.
Not enough solutes. So instead of being 26 for your OPC, you're going to be less. You're going to be less than 26. And keep in mind, we're battling that 15 to 17 for hydrostatic pressure. If you go below 15 or 17, that fluid's not coming back in. The fluid is still being pushed out. Exactly. So a person who has a liver disorder may have a bunch of their fluids stay out here in this interstitial space. What does that result in? Edema or swelling. So on Tuesday's class, we talked about filtration versus reabsorption. In order for you to avoid edema or swelling, filtration must exceed reabsorption. What kind of scenario would set you up for edema? I'm sorry, I said that wrong. I didn't like that. Filtration exceeds reabsorption is going to set you up for edema. How do you avoid edema? Let's put it that way.
Keeps you equal.
Say that. Okay, so if filtration exceeds reabsorption, then where does the fluid go? Outside. How do you prevent edema?
Have enough solutes inside of the capillary.
Have enough solutes inside of the capillary, so you need at least, say, 90% like they showed here to come back in. So we're looking for reabsorption to almost equal filtration to get those fluids back in and avoid the process of edema or swelling.
I'm confused with how with filtration, you said that it can go into interstitial fluid
Right.
outside the capillary, and how does that happen?
You're talking simple squamous epithelium for the capillary wall. That's only one cell layer thick, so that pressure behind that fluid is not going to take a whole lot to get that fluid to go between those cells and out into the surrounding space. Is that kind of what you're asking?
Like the plasma protein and the solute that is being filtered in by the HPC.
Right.
Are you saying that with the liver problems, all of the solute and the protein plasma is not getting into the capillary?
I see where you're coming from. Those plasma proteins and solutes don't necessarily leave the capillary. The proteins for one are too big to leave the capillary. We may diffuse some solutes out and then diffuse them back in, but this process counts on those solutes and proteins being in the capillary the whole ride through. So with a liver disorder, instead of having enough solutes and proteins in there to reclaim those fluids that the venous in, there's just not enough. Mainly, if it's a liver disorder, you're talking not enough proteins to pull that fluid back in. So it stays out there in the interstitial space. So the proteins are not something we're really exchanging with the environment. Does that make sense? We are only talking fluids in and out right now, not talking solutes or anything else. Barbara.
When you said filtration must exceed reabsorption, is that to prevent an edema or the...
Filtration exceeding reabsorption will actually promote edema. Yeah. In order for you to avoid edema, filtration and reabsorption must be almost equal. Like you're seeing here, 90% of it comes back in at that venous end. So you're looking at almost having the total amount that goes out, bring almost all of it back in at the venous end.
So do we just need to stay hydrated to avoid the osmotic pressure dropping?
Stay hydrated, have enough fluids, yeah. I mean, making sure that you reclaim enough fluids or at least drink enough fluids to prevent it from leaking out and staying out.
So there's something else we have to do to keep the osmotic pressure up?
If you eat a normal diet and you have a functioning liver and your solute and protein levels are normal, then that should operate as normal. But you know, if you've got a liver disorder or if you've got blood pressure issues, then you may be pushing more out than you can reclaim back, and that's where you get the edema from.
Okay, thank you.
Yeah. How are you doing with this? Is this starting to make some sense? Okay. Let me run down the questions with you on page 63 and see how you did there. The first question says, what happens to capillary hydrostatic pressure? That's just simply blood pressure from the arterial end of the capillary to the venous end. Decreases. Good. So we already knew before we covered this topic that blood pressure decreases along the length of the capillary. Blood pressure is hydrostatic pressure, so it does decrease along the length. Thankfully, there is a drop in that hydrostatic pressure because for number 2, the drop in that hydrostatic pressure is what allows for that fluid flow to return in to the venous end of the capillary. So fluid flow can come back into the venous end thanks to the drop in hydrostatic pressure. For number 3, where are plasma proteins normally found?
In the capillary.
In the capillary, good. Their job is to do what?
Pull the osmotic pressure.
Yeah, they create the pull for osmotic pressure. Your job is to pull fluids into that capillary. So number 3, those plasma proteins pull fluids into the capillary. Number 4 says, why does fluid enter at the venous end of the capillary, but not at the arterial end?
Higher HPC at the arterial.
Good. At the arterial end, notice the HPC, which is hydrostatic or blood pressure, is too high, and that doesn't allow for those solutes and proteins to pull enough fluid back in. So the battle here at the arterial end is won by a higher HPC. Okay, so at your arterial end, we're looking at a higher HPC. That's successfully pushing those fluids out.
Pushing the fluids out?
Pushing the fluids out, right.
I thought it was the other way around.
We're at the arterial end, got two pressures, right? Hydrostatic and osmotic.
Right.
Which one's higher?
Yeah.
Hydrostatic. Good. Hydrostatic's in the 30s.
Fluids.
Osmotic pressure is in the 20s. So the higher pressure here is going to win the battle. The higher pressure is going to be pushing the fluids out, and of course that's going to overcome any kind of pull to get the fluids back in. So that's why at the arterial end you can't successfully reabsorb any fluid because the hydrostatic pressure is too high. Does that make sense? Number 5 says, does osmotic pressure vary from the arterial end to the venous end to the capillary?
No.
No, it's pretty stable. Okay, so we used a value of 26 from arterial to venous end. Looks like up here they're using 22, but you get the feel that it's somewhere in the 20s. Okay, so osmotic pressure is stable from the arterial end to the venous end. So what this means is the amount of solutes and proteins inside your capillary pretty much doesn't change across the length of your capillary. So that's why it stays fairly stable from one end to the other. Blood pressure, however, does change. We call blood pressure hydrostatic pressure. That does drop across the length of your capillary. Why does it drop?
Further down the vein. And the friction from the wall.
Get friction from the wall, it's a longer vessel, you're going to lose some steam, and of course you're right, that fluid that's pushed out is going to drop that blood pressure. Okay, so yes, hydrostatic pressure does indeed drop, and it drops from the 30s, as you can see, on the arterial end, all the way down to around 15 on that venous end.